Hello, welcome to Stats 2110 at Washington State College. This is the first part of Chapter 2. We're going to talk today about frequency distributions and mostly about how to construct one, and what a distribution is, what a frequency distribution in particular is. Uh, Basically, a distribution is just a way to describe the structure of a data set or a population. Um, a frequency distribution specifically, just a moment. Okay, a frequency distribution is a type of distribution that records the frequency or how often each value or range of values occurs within a data set. Um, Frequencies are the rates of occurrence that go with the data set. So we'll get to some examples in a minute. Honestly, I don't find these particular definitions very clear myself, um, but we will get to that. So when you're dealing with frequency distributions, you frequently you're looking at counts of occurrences of some class, some category. So, for example, if we're talking about coin flips, you'd have heads and tails as your classes, the categories your data falls into, and your frequency is the number of, your frequency of heads would be the number of times you've got heads. Frequency of tails would be the number of times you've got tails. Frequency distribution would be the whole thing. Um, okay. I did want to go back and mention the other type of distribution is that they'll talk about in your book at least is probability distributions. Frequencies are used for measurement. So I've flipped a coin X number of times and recorded my my uh, my results. Probability distributions are theoretical and are used for predictions. So, and we'll get into probabilities in a later chapter. So we're not talking about them right now. So if we take an ordered array is essentially a frequency distribution that's got an order to it. Um, a probability distribution, as I mentioned, is theoretical distribution for predictions. Um, so if I wanted to predict the outcome of a coin toss, I would be using a probability distribution. Coin toss is, of course, a fairly trivial example of that. We can also have ungrouped frequency distribution. So each category or class represents a single value. So the coin toss is an example. We've got heads and tails. There's only one value that goes under heads and tails. Or if we're talking about jelly beans, because I made my notes on this when I was hungry, apparently, each color or flavor of jelly bean is an example. It would be a group. There's one value. It's a green jelly bean or an orange jelly bean. Um, we're not talking gummy bears where they can be, or half of one color and half another, and that may vary. There's one value. Um, as you might guess, the next example would be grouped frequency distribution. So there, each class has a range of possible values. So a great example for this is grades. Um, right, you've got A, B, C, etc. as your groups. The percentage score that gives you an A is usually 90 to 100. So any count value that falls under 90 to 100 is assigned to the group A. So if you have 10 A's in the class, that doesn't mean you had 10 people that got 97. You had 10 people that were in the range 90 to 100. So group frequency distributions, each category is a range. Ungrouped, each category is a single value, like a color or something. Okay, so let's talk about how you construct a frequency distribution. First off, you need to decide how many classes you need to split things into. So in the grades example, typically we've got A, B, C, D, and F. Sometimes you might not do D's. See, that's part of the decision. You have A plus, A plus, A minus, B plus. Are you including those? So how many classes go into the distribution? In this textbooks, they're going to suggest a number of classes each time. So we're not going to have to worry about that. Keep it a little simple. The next step is to choose an appropriate class width. So, sometimes it's easy. You've got years, you've got decades, you've got obvious size classifications. Grades tend to be 60, 70, 80, 90, 10 percentage points is kind of the default basic. Other times, you got to come up with something. So a lot of times you'd subtract your lowest value from your highest value and divide that by the number of classes you're going to use, and that gives you a starting point. And as we'll see in some of the examples, you usually tweak things to make it make more sense based on that. Like I said, you then go and make adjustments so it makes more sense and the data is easier to see and present. The next thing we do is find the class limits. What's the lowest value that fits in each class and what's the highest value that fits in each class? We use the same number of data points as the largest decimal places in the example. So a good example of why this is important again is grades. So if we take our lower class limit as, let's go for B's. The lower class limit is 80 and the upper class limit is 89 then, right? Because we don't want it to overlap. It can't be 90 because then if somebody scored a 90, would that be an A or a B? Because it's in both technically. If our upper class limit is 90 for B and our lower class limit is 90 for A, so we go slightly lower. However, if we're recording scores in and somebody comes up with a grade of 89.9, we've got something that falls in between that gap there. So we have to make sure we keep the same number of decimal places. So if we're going to be recording grades using one decimal place, then we need to make sure our class limits use that one decimal place as well, so that somebody who gets an 89.5 gets a grade and isn't somewhere in limbo. So we keep doing that. We usually start with either in the book they say you start with the bottom. With grades, frequently you'll start towards the top, but the bottom is probably the much more commonplace for most cases. Start with the bottom and take your class width that you've decided on and construct your class limits based on that. Then you start adding up what goes in each class. So you look at your grades and say, okay, that one's an A, let's mark that. So I've got one A, that's B, mark that. There's another A, so now I've got two A's, and just add them up until you've got the frequencies of occurrences of data points in each class. All right, so again, some vocabulary rehash. The class width is how wide that each class is. The lower class limit is the smallest number that can fit in it. The upper class limit is the largest number that can fit in it. So let's do an example. All right, so we've got this distribution. We've got this data set. These are 3D TV prices in dollars. We've got 20 TV prices here. This is how much a 3D TV cost in whatever year they publish this. This is in an ordered array. You'll note this is lowest, next lowest, next lowest, so it goes up. Next line keeps going up. Each line it wraps back around. All right, we know we want 5 classes for this, and we want to construct a frequency distribution. So let's first decide on the class width. So I want you to take a moment. Remember how they suggested doing class width, right? Highest point minus lowest point divided by number of classes. Go ahead and take a minute and do that, and pause the video while you do that. Unpause when you're ready to move on. Okay, so they've done the calculation for us. Came up with 80.8, which round up to 81. Whoop. So we've got an $81 class width. So let's think about that for a minute before we move on. How useful, if we're presenting this data, how useful would an $81 class width be? So we've got a 15.95 as our lower limit. Calculator. You remember when I said I did not have a TI 83 or 84 myself? I've got an old HP 48 instead. That's from my college days. And it does not calculate things quite this, or it's got a very different user interface. So that gives me, where's my camera? There's my camera. That gives me 1676. So my lower class would be from 1595 to 1676. If you think about how if you were thinking about presenting this information to somebody, is that a way they'd really want to look at it? Probably not. You're not used to thinking in weird units like that. It's starting in kind of a weird spot. It's ending in a weird spot. It's just going to get weirder from there. So it'd be more reasonable to go with something that's a more round, even number. In this case, 100 would work. It's 81 is reasonably close to 100, and 100 is a term we're used to working in. So we'll go with 100 for the class width. It's just more reasonable and will give us a nicer presentation. So let's talk about the lower class limit. When it started at, our lowest value is 1595. Is that, and we've got a width of 100. Does it make a lot of sense to go from 1595 to 1695? Well, 1694 to 1794. Sorry, 1695 to 1794 and on. Not really. It's going to look nicer to go 1500 to 1599, 1600 to 1699. It's a more natural break, more natural way of looking at things, presenting things. So we'll start at 1500 and we'll go from there. So let's build our class limits. We'll add 100 to 1500. We get the next lower class limit of 1600, and etc. to determine the upper class limits, we've got our 5 classes, so we need to determine the upper class limits. We want it to be reasonable, and classes are not allowed to overlap, right? So if we look back at our data, that's all in whole dollar amounts. So we're not going to want to do $15.99 and 99 cents. It wouldn't matter. We don't need that 99 cents. So we'll go with whole dollar amounts. We'll just go slightly lower, and we'll be at $1,500 to $15.99, etc. In this case, the upper class limit also ended up being the maximum. That's not necessary. We've got all our data values in our range of classes, so we don't need to adjust anything. And there we go. We've made a nice table. We can record the frequency of occurrence in each data point, and we come up with this nice frequency distribution. Now, something we really should do to go back and check, remember we had 20 data points. How much do we have here? We've got 2 plus 5. Well, 5 plus 5 is 10, 4 4 is 8, and plus the 2 makes another 10. So we've got 20 data points there. We're good. We've included all the data. We didn't accidentally miss something somehow. Okay. Next thing is a class boundary. So this is kind of a theoretical point that sits halfway between the upper limit of one class and the lower limit of another. And what this is really used for is producing bar graphs of your distribution where you don't have any sort of gap between your classes. Obviously this is something you only need for numerical data. We couldn't. Well, actually, all of this frequency distribution portion we're talking about right now only matters with numerical data. If we're using categorical data like jelly bean colors or coin flips, that the groupings are fairly obvious, and we don't have class widths and stuff to worry about. That's different. Okay, so the class boundary, again, just halfway between one class and the next. Easiest way to calculate that is to add them together and divide by 2. So in our case, we get 1599.5 for our first one. Then we can just add our class width to that to get the next one. And when we do that, if you want to take a minute and do that, I really should have had you pause and take a minute to construct the frequency table yourselves. So take a minute and do that. You can subtract 100 to get the lower boundary that you would have started with. Add 100 to get the upper boundaries. Take a minute and do that, and unpause when you're ready to move on. And check to see if your table results match these ones. Okay. The next thing that's a part of a frequency distribution is the class midpoint. This is, if you add the lower limit to the upper limit and divide by 2, you get the midpoint in the class. It's a good way to kind of report the average value for a class. It also is convenient for creating certain types of graphs from your frequency distribution. So if we were to do that for our data, again, we're adding the lowest to the lower class limit to the upper class limit and dividing by 2 to get our midpoint. Then take a moment and add that to your table, and unpause when you're ready to move on. So we can do that. We get we get our values. You could do just the one midpoint and then add the class width to it each time. That works as well. Okay. The next concept for frequency distributions is relative frequency. So this is the percentage or fraction of the data set that falls into a particular class. So it's just our frequency that we found divided by the total number of samples we have. So in our case, here we had 20 samples. So if we divide all of our frequencies by 20, we get our relative frequency. So if you want to take a moment, calculate the relative frequencies for each value on that table, and then unpause when you're ready to proceed, and I'll leave it on the next slide for a few minutes so you can check. Okay. Now again, at this point, a good thing to do would be add these. Let's see, do I have a highlighter? Display settings. There's my highlighter. It's hiding under my screen capture bar. There's my highlighter. Pin. If we add these, come on. If we add these relative frequencies up, we should get 100. Sometimes you will want to round these so you get nice numbers that are easy to present, but they've got to add to 100 at the end. Otherwise, you've done something really screwy. So, in this case, the data naturally forms nice, easy numbers, partially because there's 20 data points there. Turn my pen off. There we go. The cumulative frequency is the sum of the frequencies in a given class. This is most useful if you're in an ordered list like we have right now. So if you want to take a moment and come up with the cumulative frequency for your table, we're not doing a cumulative relative frequency, just the raw frequency. So I'll do the first one as an example. We've got in 1500 to 1599 we've got 2. In 1600 to 1699 we've got 5. So our cumulative frequencies would be 2 in that first batch, and then 7, which is 2 plus the 5 that's in the second batch for the second batch. Go ahead and do that and unpause when you're ready to move on. And give you a minute to check. You can see where the numbers came from. We're just laser pointer here. We just take the cumulative frequency above, add the frequency for the one we're into it, then we take that cumulative frequency, add that one to it, take this cumulative frequency, add that one to it to get 16, etc. Oh, I can put in the laser pointer right there. Nope. There we go. Okay. So let's move on to another example. So if we're looking at some data for the number of miles that professors drive to work, and we want to do 6 classes for this, we want to create a frequency distribution that includes the boundaries, the midpoints, the relative frequency, and the cumulative frequency for each class. Remember, the boundaries are the values that are halfway between the class limits. Want to double check that our class limits have the same number of decimal places as the largest number of decimal places in the data, so we don't have stuff that falls in between classes again. So here is our data, and they've gone ahead and done the first estimate for class width right there. So let's stop here and think for a minute. We've got our data is not ordered clearly, so we've got there's our lowest point there is 1. Our highest is that 11.9 there. Go ahead, get the laser pointer back. There we go. There's our lowest. There's our highest. We subtract those, divide by 6, and round to the 1 decimal place we're using. We get a 1.8. 1.8 isn't really unreasonable. It probably would be more sensible to use a whole number for miles driven. So let's go with 2 instead. So let's pick our lower class limit. As I've already advanced the slide because, and they give this discussion right here. The smallest value in this case is 1. The smallest value is a good place to look at for our starting point. In this case, it is a good starting point. So we've got our starting class, lower class limit of 1 and a class width of 2. So if you want to take a moment and build the lower class limits and upper class limits for the 6 classes, and then pause while you're doing that and unpause when you're ready. Okay, so this is what the book came up with. Again, our class width is 2, so our lower class limit for the first class is 1, the next one is 3. They've backed off just 0.1. We're using 1 decimal place in the data, so it's our class limits have that 1 decimal place as well, so it matches. Our highest value was 11.9, so everything falls within those within this range, so we don't need to adjust anything for that. The next step they do is to do the class boundaries and midpoints. So let's go ahead and take a moment to do that. Remember, so to find your first class boundary, you take the upper boundary of, the upper limit of your lowest class and the lower limit of the class right above it, add them and divide by 2 to find that first midpoint. Add your upper and lower class limits for that first class and divide by 2. So you go ahead and make a column in your table for that. Do the calculations and unpause when you're ready to move on. And actually, please go ahead and find the frequencies while you're at it. Go ahead and find the frequency, relative frequency, and cumulative frequency, and we can check it all at once. Okay, there we go. We've got our class boundaries, our midpoint. There's the relative frequency, so that hopefully all of you remember this, but that bar over the 6 there means it's 6 repeating. So this is 1.666666, so that would round up to 17. There's our cumulative frequency. Let us check. Let's see, we had, how many data points did we have? We should check make sure this is correct here. There's our data. We've got 1, 3, 1, 2, 3. We've got 18 data points in our data set here. Oops, there we go. So let's see, 3, 6, 10, 12, 16, 18. So we've got that right. 17 is 34, 56, 67, 89, 100. Okay, so it adds up to 100%. So that works. Our cumulative frequency, this here at the top should be 18. It should be the number of data points we have as well. So that checks out also. It's always good to go back and double check things. I know it's very easy to drop something in a calculation. So if you can build in checks, that's always a bonus. Always a good practice. So let's review. To create a frequency distribution, you first decide on the number of classes. Usually it's between 15 and 20 to be useful and not just be... I mean, the point of this is somewhat to condense the data into a more usable form. So if you have more than 20 classes, it's less useful. Next step is to choose an appropriate class width. The highest value minus the lowest value over the number of classes is a good starting point. Then you adjust that to something that's reasonable. Class limits. You can either start with the lowest data value, or if something below that is more reasonable, you go to a smaller number that's more reasonable. If your lowest limit is 13, maybe it's more reasonable to start at 10. If it's 12, if it's 10.52, maybe it makes more sense to start at 10 still, just because it's a more comfortable, easier to present view. And then you count the number of data values in each class. That's your frequency. You find the class boundaries by splitting the difference between in the gap between the upper limit and lower limit of two classes. Find the midpoints as basically the average of the upper and lower limit of each class. Relative frequency is the frequency divided by your sample size. Cumulative frequency is the sum of frequencies for a class and the previous classes. Cumulative frequency really makes most sense in some sort of ordered data set. Okay, that is it for... Kill my laser pointer. That is it for this section. Get up, take a break, do whatever you need to do, and then get to the next one in a bit.